Our next speaker, Mark Mackaman, is the product manager for OS/2 and system software, where he has overall responsibility for all aspects of OS/2, including the software development kit or SDK. Mark's broad overview of the technology is crucial to your understanding of OS/2. He will be introducing you to the many new concepts and terms that will be discussed in greater depth in the remaining talks of the conference. He has also been instrumental in assisting me in developing the agenda for the conference.
The purpose of my presentation is twofold. The first is to provide an overview to Microsoft Operating System 2, the new operating system for advanced personal computers. The second purpose is to introduce key concepts and terminology that's going to be used throughout this conference. As you can see from the slide, Operating System 2 has a graphic user interface. It's very similar to our current Microsoft Windows product for the DOS environment. The major difference is overlapping windows, as evident on the slide. Other than that, there's very few changes between the windows that we have today and the windows for the presentation manager. With OS/2, the presentation manager and the kernel are combined as one, integrated as a whole for one product. Other features of Operating System 2 include enhanced usability over the DOS product, usability features such as an online help, and other easy-to-use features of the product. With OS/2, we allow concurrent processing of multiple applications. Another terminology used for this is multitasking, the ability to run multiple applications simultaneously within a single personal computer. And the product exploits the 286 and 386 real and protected modes, and I'll describe what these are in just 1 minute. Some other features include OS/2 runs most DOS applications, preserving users' investment in application software. Unlike the DOS environment where we use software interrupts, in OS/2, programmers use a call-based interface for calling the operating system. OS/2 has a structured architecture. This allows the operating system to be broken up into components, making it easier for Microsoft to produce subsequent releases. It also allows a structured architecture of your application. Instead of having this one module that you had to do under a DOS, MS-DOS or PC-DOS, under OS/2 you can develop an application that's structured in its architecture. The open system philosophy continues with OS/2. We've published the information. We've provided software development kits so that application developers can begin learning how to write applications for OS/2. And there's this opportunity for application developers. Just as when we moved from CP/M to DOS, there was a new environment in which to develop applications. A new opportunity was presented under DOS. So will it be with OS/2. When we move from DOS to OS/2, there's this opportunity for application developers to produce a new generation of applications, this third generation of applications for OS/2, exploiting the special features and enhancements that we've provided in the OS/2 environment. To understand how OS/2 is constructed and how it works, you need to have a little bit of an understanding of the hardware architecture, since OS/2, the operating system, interacts more closely with the hardware than it did in the DOS environment. As you can see from the slide, there is two types of or modes of operation within the Intel processor family, the real mode and the protected mode. The 286 and 386 processors support both real mode and protected mode. The 8086 only runs in real mode. OS/2 requires both the real mode and the protected mode environments. Therefore, OS/2 only runs on 286 and 386 based personal computers. In real mode, there's no system integrity due to the absence of hardware protection. In real mode, an application can address the full address range from 0 to 1 megabyte. Therefore, there's no hardware protection, which means that any application can address anywhere within that physical address space. The chip's architecture, the real mode architecture, allows only 1 megabyte of addressability. And due to the way the PC was architected, this is further reduced to only 640K. As I mentioned before, applications can access hardware devices directly. All they have to do is write to those specific memory addresses, and they can talk to those hardware devices directly. And as you all know, DOS runs in this mode. Protected mode is the new mode that we're exploiting with the OS/2 operating system. With OS/2 in protected mode, the system integrity can be assured because the hardware provides support for protection. The hardware assists the operating system in isolating physical memory from the application. In addition, in protected mode is where we get the large address space of OS/2. For the 286, that's 16 megabytes of real memory and 1 gigabyte of virtual memory. That means applications are not limited to the 16 megabytes, but can address the whole virtual gigabyte address space of the 286 environment. We also take advantage of, we also run on the 386 in supporting 4 gigabytes of real and 64 terabytes of virtual memory. Many of us said before when we moved from CP/M to DOS, when we moved from 64K to 640K, we said, who could write an application that would take up 640K? Yet you've done it. We're now up against the 640K limit. And OS/2 for the 286 and 386 processor will allow applications will unleash applications and allow us to take advantage of this greatly enhanced memory address space. However, in protected mode, applications must use the operating system to access the hardware devices directly. And this is because in protected mode, an application can't address physical memory. It must go through the operating system. As you can see, we use a ring architecture, or the 286 and 386 use a ring architecture for controlling protection. In the center at ring 0 is the OS/2 kernel. Ring 1, we have nothing running, and ring 2 is special purpose I/O and part of the presentation manager. And ring 3 is where the applications run. The way the protection ring is implemented is that anything in the inner rings can access anything on the outside rings. However, anything running on these outside rings cannot access inside. Therefore, its protection is implemented. The OS can access anything outside, but the applications running at ring 3 cannot access the operating system unless they go through call gates. Some of the system requirements, obviously a 286 or 386 based personal computer, at least 1.5 meg of memory, a hard disk for storage, application storage, system software storage, as well as we use it as a swap device. There's a high-density diskette drive required in which to initially install and boot the system, and a graphics display and adapter to run the presentation manager. With that brief hardware overview, I now would like to review the application environment and then the system structure, how the system is put together. But let's first look at it from an applications perspective. This is a memory layout of the PC. 0 to 640K is what we call the DOS compatibility mode. This is where DOS applications run. 640 to 1 megabyte is still reserved, and 1 megabyte to 16 megabyte, or however much RAM is installed within the PC, is the protected mode memory. This is where protected mode applications run. There's a movable boundary in the DOS compatibility mode that allows the user to select how much memory they want allocated to the compatibility mode. It can be set anywhere between 0 and 640K. If it's set lower than 640K, that additional memory is used as protect mode memory. If the user sets that at 0, the system is now completely a protect mode system and will not be able to run run DOS applications. The DOS compatibility mode, or the real mode, allows one DOS application to be run at a time. The documented DOS 3 API is supported, and very few of the undocumented API calls are supported. A couple of the examples of the ones that are the undocumented calls that are supported are the NDOS flag, for example. In the DOS compatibility mode, the applications run just as they do under DOS. That means to obtain system services from the operating system, they utilize the software interrupt 21, for example. As I mentioned before, there's a flexible environment size, allowing the user to set how much memory is used for real mode. One disadvantage of this environment is that applications running in the compatibility mode are suspended when they're in the background. They run normally when they're in the foreground, which means when the user is interacting with them, but they're suspended when they're put in the background. The protected mode is the new mode for operating system 2. This is where OS2 applications can exploit the advanced features of operating system 2. The user switches between real mode and protected mode. It can't be done under program control. The new operating system 2 applications continue to run in the background, unlike their DOS counterparts. The system may be protect mode only, and that's done via a config.sys entry, setting up the system to be protect mode only, thereby protecting the system. The system function request, or how an application obtains services from the operating system, is different, as I said before, under OS2 than it is under DOS. Under OS2, applications use a FAR call to dynamic link libraries or dynamic link API. And I'll get into this in just a minute. Device drivers for OS2 are new as well. This is necessitated by two things. The first, because we're switching the processor between real mode and protected mode back and forth to run DOS applications, the device drivers need to be able to take and process interrupts in either mode. This processor could be in protected mode or in real mode when the hardware interrupt comes in. Therefore, device drivers need to be able to handle this bimodal environment. The second cause for new device drivers are because it's a multitasking system. There's going to be multiple applications calling to the device driver simultaneously. Therefore, device drivers need to be able to handle multiple calls simultaneously to its strategy routine. Now to review system structure. As we can see in the bottom of the chart, there's the hardware, and device drivers talk to the hardware just as they do under DOS today. Between the 0 and the 640K is where system low along with the device drivers reside. Up from there is the compatibility mode. 641 megabyte reserved, as I said before. And then the low part of high memory, the 1 megabyte and above, is where the high part of the operating system resides. This is where the parts of the operating system that service the protect mode applications only reside. The design of the system was, in the low part would be those pieces of the system that are needed to run both the compatibility mode and the protected mode. And what's up on high, in the high part of memory, is just those pieces of the operating system to support the protected mode applications. This is a diagram of the system structure. First, going through the compatibility mode, you see a DOS application. The DOS application calls DOS. It's really not DOS, MS-DOS, but it's an emulation of DOS 3.3. That in turn either calls the BIOS, or an application can call the BIOS directly, just as it can under DOS today. In addition, the DOS application can call the hardware directly, just as it does under the DOS environment. However, in protected mode, it's a different type of system architecture. The OS2 applications call a dynamic link application program interface, or API. This is just a set of dynamic runtimes, if you will, for the operating system. And in turn, these call the kernel, which in turn may call the device drivers in the BIOS, which in turn would call the hardware. In OS2, we can't use the ROM BIOS installed in the machine in protected mode. There's too many things that are counter to using it in the protected mode, such as wait loops, and it does some software interrupts of its own, which are not permitted in the protect mode environment. Therefore, the device drivers contain a lot of the functionality that's in the ROM BIOS today. Therefore, OS2 is more closely tied to the hardware than it was under the DOS environment. But yet, on the other hand, it's because of the operating system talks directly to the hardware, there's not this incompatibilities that we experienced between the different versions of DOS. There is also a capability for an application to talk to the hardware directly. This is through what we call an I/O privilege level segment. This is a segment or a code segment that runs at ring 2 that allows an application to talk directly to the hardware. Again, though, it's through the operating system that they can talk directly to the hardware. As a brief review, I've talked about the hardware environment and its implication on the OS/2 operating system. And I talked a little bit about the applications environment, what the environment looks from how the environment looks from an application's perspective, and I talked a little bit about the system structure and how it's architected and how the pieces fit together. Now I'd like to talk about the system foundation. What are the key components of the operating system and how they work and interact together? I want to talk about the system function request, dynamic linking, multitasking, memory management and protection, inter-process communication facilities or IPC, graphics, screen groups, and I/O services. All of these subject matters will be covered in a future presentation or a later presentation. So I'm just providing an overview of the concept and introducing some of the terminology. System function request or application program interface. How the application obtains services from the operating system is through FAR calls to the operating system. We don't allow software interrupts under the protect mode environment. Using a call-based interface allows applications to be portable between real mode and protected mode, and I'll describe how you can do that in just a minute. It also conforms to the standard linkages of high-level languages, and using this call interface, we can dynamically link to the operating system. All the parameters are passed on the stack, all error codes returned in AX, and all functions remove their parameters from the stack. These are all just standard features of the protect mode environment. As I mentioned before, by using this call-based interface, we can make applications that are portable between the OS environment, OS/2 environment, and the DOS environment. By having an OS/2 application adhere to a subset of the whole OS/2 API, you can make applications that can run in the DOS environment, the OS/2 compatibility environment, as well as the OS/2 protected mode environment. The way this is done is by creating a family application, an application that uses a family API subset of the total application program interface. By using this call-based application, as you can see by the center box, there is this family API, you have a stub loader, and then you have bindings. When you build a family application program, you go through the compile, the linking, just like you did before, but you go through this third step called binding, where we put a stub loader and the bindings on the end of your application. What happens is when this application gets loaded into the DOS environment, either under DOS or the DOS compatibility environment, your application gets loaded in, but the bindings as well. All the bindings are subroutines that do the software interrupts. So for example, if in your family application, if you did a call DOS open, instead of calling directly to the operating system as it does under OS/2, what happens is that call is rerouted to the bindings, which is the subroutine that does the software interrupt in the DOS environment, which is comparable to the call DOS open. When this same application is loaded into the protect mode environment, the stub loader and bindings are ignored because the family application is tailored for the OS/2 environment. And so there's not all the unnecessary code and execution that goes along with running a family application in the protected mode. Dynamic linking is a new concept, but it's similar to the Windows dynamic linking concept. And as all this is the delayed binding of an application's external references to its subroutines until load time or run time. All system function requests are done via dynamic linking. As a pictorial of what's going on, as you can see from the chart in the upper left-hand corner, where your source contains the call, for example, call DOS write. You go through the compile process, and your object code, it's still an unresolved external reference. When you go through the link process, The linker is smart enough to know that this is a call to a DOS dynamic link library, and it goes looks for that dynamic link libraries, and then it's an entry point that calls entry point into that module and does a fix-up at that point. However, the module, the dynamic link module, is not linked into the exe, but instead just contains a reference to that entry point in that module. When that application executed, the call DOS write, when that is called to the operating system, if it's not already loaded in the system, the operating system will make a call to the kernel and the device drivers to load it in from disk and to place it into the dynamic link API. Then the application continues to run because now the call DOS write is loaded. If subsequent applications make that same call, say for example the call DOS write, it's already loaded. So there's no going out to disk and loading in a separate copy of that. In fact, all that happens is when it makes the call, there's a fix-up and says it's the second call to that interface or to that library, and that a counter is incremented, but in fact a second copy is not loaded in. It uses the same copy that's already resident in memory. Some of the benefits of dynamic linking is it allows Microsoft or ISVs or other application developers to extend this application program interface by providing their own dynamic link modules and the code that supports that underneath. Since the dynamic link libraries are shareable code segments, now applications can be much smaller. The exe sizes can be smaller because commonly used code can be put as a dynamic link module and not linked into every application that they produce. It provides faster loading for the second and third instance of the use of that dynamic link API. The first, as I mentioned before in the previous slide, it still has to go and load that dynamic link module from the disk into memory. But subsequent applications, when they make a call to that same dynamic link module, are much quicker because that code doesn't have to be loaded off a disk. And as I mentioned before, there's a capability to do demand loading. Instead of loading all the dynamic link modules in whenever the application is loaded, they can be loaded in at runtime. One of the benefits of this, for example, would be a 3270 communication program where it needs to load in some error routines when it has a host communication line error exception, for example. Instead of providing that as part of the standard code that's linked into the exe, that can remain out on disk until it's really needed. When the exception occurs, the application can load that code in, do the processing, and then discard that dynamic link module since it's no longer needed, thereby providing this demand capability of loading these modules in, allowing you greater flexibility in designing your application. As I mentioned before, you can extend the API. And the way this is done is by providing new dynamic link libraries as well as to extend the kernel functionality, but by providing your own functionality underneath. Multitasking, or running multiple applications simultaneously. We've chosen two terms that you need to understand that will be used throughout the next few days. Those are process and thread. A process is just an instance of a program execution. A process owns resources. However, a process is not executed. What's in fact executed is a thread. A thread, there's at least one thread per process. The thread is just the dispatchable entity used by the operating system to schedule that process. Pictorially, a process owns resources. A process owns threads, memory, disk files, as well as devices such as a console. It's the threads, however, that actually execute within the system. Again, the process is not executed. Because we have a multitasking system, there has to be a task scheduler. We schedule based upon threads, and there's a priority system with preemption within the system. Obviously, you'll need time slicing, but it can be disabled by the user. To make sure that the system is configurable to a wide range of applications, we allow the user to set the maximum and minimum time slice values, as well as to set the maximum wait time that any application will wait before it is executed. The task scheduler has 3 priority classes: time critical, regular, and idle time. The time critical being the highest class. There's 32 priority levels within this class. By scheduling or by making any one thread have the same priority level within the time critical class, those are scheduled on a round-robin basis. But other than that, they're scheduled on a priority basis. Regular class is where we see most applications running. Again, 32 priority levels. A little bit different than the time critical class and the idle time class that I'll talk about in a minute, is that regular class applications, their base priority is varied based upon the I/O and CPU utilization. There's also dynamic variation of priority based upon if it's a foreground application or a background application. Again, the user interacting with the system will demand a much better response than if it's running in the background, and therefore we bump up the priority of any foreground task. There's also this maximum wait value that any application can be denied use of the CPU. Idle time is the lowest class. Again, 32 priority levels and round robin within a level. These are where idle time processes should go, such as background file transfers or print spoolers. Memory management is new for OS2. In OS2, we use a virtual segmentation memory management scheme. This means that any one program can be larger than the physical memory installed in the machine, or all the programs together can be greater than physical memory. To be able to manage memory, we move segments around. Again, that's the beauty of having a virtual memory management system versus the physical memory that we had in the DOS environment. We also swap inactive segments to disk, thereby freeing up memory, and we allow applications to explicitly load modules, as I talked about before, the dynamic link modules. Again, both swapping and movable segments can be turned off by the user, thereby locking everything in physical memory. Some of the inter-process communications facilities provided by OS2 include a clipboard, dynamic data exchange, pipes, queues, shared memory, semaphores, and signals. The presentation manager provides the top 2, the clipboard and dynamic data exchange. Clipboard allows the cut and pasting of text and data from one application to the other. Dynamic data exchange, or DDE, allows hot links between presentation manager applications. That allows one application to send messages, real-time messages, between applications. The kernel provides pipes, like Unix pipes, or Unix pipe type functionality from writer to reader. We also provide queues, which allows multiple writers and one reader. Queues can be based upon a FIFO, a LIFO, or a priority scheme. There's shared memory between applications, allowing applications to share segments between them. There's semaphores, both system semaphores and RAM semaphores. RAM semaphores being local to a process, allowing threads to signal and to exchange information. System semaphores being a global-wide system resource that allows processes to interact or to send messages back and forth, or to signal back and forth. And the last is signals, which is a primitive type of sending messages between applications. They're sending flags between applications. It also allows an application to control whether or not they want to handle the control break processing, or if there's an exception on the numeric processor, for example. We provide a complete set of graphics for OS2, both vector graphics and raster primitives. We provide windowing, as I showed on the first slide. And using this windowing environment, it's a device-independent environment, allowing the application to be independent of what physical devices that are out there. It supports intelligent devices such as PostScript printers, and it has powerful font and text handling ability. And we've added a new feature called Segmented Graphic Store, which will be explained later on in the conference. Another concept that you need to understand are screen groups. Screen groups are a virtualized screen and keyboard and mouse input into the system. Because an application can't write to physical memory, we have to manage the interaction of an application with its screen and keyboard. And we do that via screen groups. Screen groups are just the full screen, or virtual full screen and keyboard interfaces. Within that, the Windows Presentation Manager runs as one screen group. All of its windows and all of its applications all are within this one single screen group. Another screen group is the DOS compatibility mode. Because the DOS application must run in a full screen environment, we provide this virtual screen in which it can write to the physical memory, or physical display memory and keyboard. And there can be other screen groups as well in the system. These are typically for character-based applications that want a full screen interface in the system. Some of the I/O services provided by operating system are video, keyboard, communication, and mouse. The video I/O functionality follows pretty much the functionality of the BIOS N10. Again, it's implemented via dynamic link libraries, which allow the video system to be replaceable. The Presentation Manager replaces the base video system in the kernel, for example. The keyboard follows the structure and functionality of the DOS 3 and the BIOS Interrupt 15, and it too is implemented via dynamic link library, allowing it to be replaceable as well. Additional I/O services are that we provide support for the Microsoft mice, and it follows the structure of DOS 3.3 and the extended calls that were provided under the DOS 3.3 environment. Again, it is replaceable. The file system is very similar to DOS 3.3, and in fact is 100% compatible with the DOS environment. This means that we have the same limitations that we do under DOS 3.3 today. We have extended multiple logical DOS partitions. However, each one of these partitions is limited to 32 megabytes, just as they are under DOS 3.3 today. We will eliminate this restriction in one of the early updates, or one of the early versions of OS2. One of the other unique features that we provided within OS2 for I/O is character device monitors. A character device monitor allows an application to intercept the data stream between a character device and its application. Therefore, this is a mechanism that you use to make terminate and stay resident type functionality, or TSR type functionality, in the OS2 environment. There can be multiple device monitors within the system, and they're on a per screen group basis. Therefore, in one screen group, you can run one type of monitor, and another screen group, you can run another set of monitors, depending upon what type of applications are running in each one of those screen groups. Quick review over the system foundation. We talked a lot about the kernel and some of its features, dynamic linking, multitasking, interprocess communication, graphics, screen groups, I/O services. What I'd like to go into now is an overview of the Presentation Manager, or the user interface for the OS2 product. As I mentioned before, it's a full function graphic user interface. It's the same interface, or the same user interface, as we have for Microsoft Windows 2.0, and it replaces the command line interface just like it does under Windows today. One of the features that we added to OS2 is a program selector, allowing the user to select from a list of installed applications what applications the user wants to run. It also allows the user to switch between the multiple applications that are running in the system simultaneously. With the Presentation Manager, there will be a desktop, or a Presentation Manager desktop, that will provide some unique and enhanced features to the system. One of those is a visual, structured view of the file system, different from just doing directories under the base system. Some of the features of the Presentation Manager are pull-down menus, dialog boxes, pop-down message windows, scroll bars, and push buttons. Manny Bellin will follow in a future presentation. We'll go through each one of these areas in detail, explaining what they do and how they're used within the system. Now I'd like to review the different types of applications that can run in the OS2 environment. First, the DOS applications, and then the OS2 applications. And there's really two types of OS2 applications. There's the presentation manager applications, and then there's what we call character-based applications, or applications that talk to the kernel directly and do not use any of the services of the presentation manager. This is where the applications run. In the lower part of memory runs the DOS applications. Again, one DOS application runs. In the 1 megabyte to 16 megabyte protect mode environment is where the Windows Presentation Manager runs and its Windows applications, along with the character applications or kernel applications, which run in separate screen groups, but all run simultaneously within the protect mode environment. DOS applications, most will run, including the ill-behaved, applications that write directly to the physical memory. Those that won't run are the ones that are timing dependent, communication type programs, because when they're put in the background, they no longer receive hardware interrupts or clock interrupts. Because they don't receive these interrupts in the background, they most likely will not work properly. Network applications. When I originally put together these slides, I didn't think many network applications will run. However, from our practical experience, a lot of network applications run. The applications that utilize the NetBIOS or Interrupt 5C seem to work okay in the DOS compatibility environment. However, applications that take advantage of some of the extended API calls, like the extended interrupt 2A and 2F, may not work properly within this environment. Another class of applications that won't run in this environment are those applications that know something about the operating system or know something about DOS. It's applications that go in and look for a DOS data structure or go in and twiddle some bits within DOS probably will not work in this DOS compatibility mode. The reason is it's not DOS 3.2, for example, that's running there. It's a DOS emulation. So the data structure may not work. That data structure may not be there, or it may be in a different place within the operating system. It's the same problem that we had moving from DOS 2 to DOS 3 in that a lot of applications broke. However, I'm looking to you, the application developer, to help us both identify those problems, things that you need to find out about the operating system, either so that we can provide you with an external way of getting at that information, or a way that we can help you design your application so you don't need that information. An example would be Windows 1.03 doesn't work in the DOS compatibility environment. The reason, it went in and looked for certain DOS data structures. However, the Windows 2.0 product does run in the compatibility environment. Therefore, if we can do it, and Windows being as sleazy as it is, I'm sure that we can help you get your application to work in the new DOS compatibility environment. The last type of application that will not run properly are those that use a form of copy protection scheme that writes to absolute hard disk locations. The reason these won't work is the operating system we've disabled this functionality. The reason being is that because another application may be running that needs to write to the disk, the operating system may write to that same physical location as you are trying to do with your copy protection scheme, and therefore will have a collision and a potential loss of data. Therefore, we've not allowed absolute writes to hard disk locations. However, you can do absolute reads and writes to the diskette drive. Therefore, key disk type of copy protection schemes do work properly in the OS2 environment. Microsoft Windows 2.0, as I mentioned, runs in the compatibility mode. Therefore, Windows 1.x and 2.x applications, multiple copies of these can be run in the compatibility environment. The presentation manager applications, this is the first type of applications that run in the OS2 environment, utilize the presentation manager API. They do not use the kernel API, but they use the presentation manager API. We believe this is the application program interface of choice, that this is the one to write these new applications for the OS2 environment. These presentation manager applications are very similar to existing Windows applications, similar in that they use the same programming model. In DOS and OS2, character applications or kernel applications use this top-down type of structure. A Windows programming model is different. It's necessitated because of the windowing environment that we must use a message loop-based architecture, which is completely different from the top-down architecture for DOS and OS/2 kernel applications. And we'll get more into that in day 2 of the seminar. And both character and graphics applications should use this new interface. Several people have said, well, I want to write a character application, so I don't need the presentation manager. And our response has been, well, why not take advantage of some of the rich text, for example, that we can provide as part of the presentation manager interface. There's a lot of functionality and benefits to the presentation manager for both graphics and character-based applications. Character-based applications or kernel applications, applications that write to just the kernel interface, they run in protect mode only. They can't run in the DOS compatibility environment unless they use that subset, as I referred to before, the family API, allowing them to run in both the compatibility environment and the DOS environment. These applications may run in a window if they utilize a certain restricted subset of the kernel API. If they go outside of that, such as they write to the physical buffer of the display or they switch the modes of the screen, they must run in their own screen group. However, in any event, they cannot utilize the Windows unique features that are provided by the presentation manager. As I mentioned before, the character-based applications must utilize a subset of this new OS/2 API. They must use the kernel interface, which is known as VIO, or Video Input Output. In the following presentation, we'll get more into how to write applications using this interface. And by the name, they're typically character only. The reason being is if they write to the physical memory and they write and do graphics to the screen without the presentation manager, then they're pretty much limited in their functionality when the presentation manager is also resident in the machine. Quick review. We talked about the user interface, which is the presentation manager, a graphic interface. We talked about the different application types. The DOS applications, again, preserving the user investment in existing application, as well as the OS/2 applications, the kernel application or character-based applications, and the presentation manager applications.
For additional information on the topic we just covered, be sure to take a look at the written questions and answers that accompanied this video tape.